Okay, we're in section 3.3 here. This is the last section of chapter 3 that we're going to cover. In fact, it's the last section of chapter 3 altogether. And this is going to be a very short section for us. And that's for a couple of reasons. First of all, in this section, we're talking about modeling with systems of first-order DEs. So the last two sections, we've been looking at application problems, where we were applying the techniques of Chapter 2 to solve those application problems. 3.3 is a little bit different in the sense that we're not going to develop any techniques for solving systems yet. In fact, we're not going to do that for quite a while. That's Chapter 8 for us. All we're doing here is coming up with systems that represent physical phenomena, systems for these applications. It's kind of like Section 1.3, where we just came up with a bunch of mathematical models and didn't actually solve any of them. We just wanted to see what that process of coming up with the DEs looked like. So it's the same idea, but with systems in this case. So that's one of the reasons it's going to be a shorter section for us, because we're not taking the time to go through and solve any of these. But it's also going to be short because we're not covering all of the applications that are covered in the book. Your book covers, well, let me just say this. We're covering two types of applications today. We're going to be looking at mixture problems, and we're going to be looking at electrical circuits. Your book also goes over, in addition to those, radioactive series, and it also talks about predator-prey models and competition models. So that kind of fits into the population dynamics application that we talked about. Those are also interesting applications, but we're just kind of we're going to get through this section pretty quickly, and we're just looking at these couple of examples. So with that said, we're specifically focusing on first-order DEs, as the name implies, as the title implies, I should say. And a system of first-order DEs can take this form. dx dt equals some function of t, x, and y. dy dt takes is equal to some function g2 of t, x, and y. They don't always have to have this form. The dx dt and the dy dt don't have to be isolated. We can have more than two equations. In fact, our very first example that we look at will be a system of 3 equations as opposed to 2. But this is just kind of a general idea of what these systems might look like. In particular, if these functions here, g1 and g2, take these forms, so a constant times x plus a constant times y plus some function of t, another constant times x plus another constant times y plus some function of t. In these cases, we refer to these equations as linear, and we would say that the system is a linear system of differential equations. Otherwise, we would say that it's nonlinear, okay? So that terminology is important, especially when we get to Chapter 8 and we start looking at solution methods for these things. But what we want to do is take some of the applications that we've already talked about and make them a little more complicated. So mixture problems, we're going to start by looking there, okay? Here's an example. It says, given this diagram right here, we want to construct a model for the amount of salt in pounds, which we're going to denote x1, x2, and x3 for the tanks A, B, and C respectively. Okay, so we're getting all of our information in this problem out of this diagram. Now what we have here are 3 tanks, A, B, and C, and in each of these tanks we're told that we have 100 gallons, 100-gallon volume in each one. And what we're going to be doing is looking at these the same way that we did mixture problems with a single tank, where we look at the rate of flow of salt into the tank and the rate of flow of salt out of the tank. And what we're going to do is make note of a couple of things here. So here's one thing I want to point out. Let's look at each of these tanks individually and notice that for any given tank, we have one or more sources of fluid flowing in and one or more places where fluid is flowing out. And there's sort of a conservation thing happening in this example. What I mean by that is that each tank is going to remain at 100 gallons at all times. And here's the reason why. Let's take a look at tank A. ignoring the fact that, ignoring whether we're looking at pure water or a mixture, let's just look at the rate of flow of fluid in each case. So in this case, we have 4 gallons per minute of fluid flowing in from here, and 2 gallons per minute flowing in from this direction, which is a total of 6 gallons per minute flowing into this tank. But then down here, we have fluid flowing out of the tank at a rate of 6 gallons per minute as well. So 6 gallons per minute in and 6 gallons per minute out. The volume of the solution in this tank is not increasing or decreasing because it zeroes out. Same thing happens in tank B here. Notice where you're following the arrows to see which direction things are flowing. We have 6 gallons per minute flowing in from here, 1 gallon per minute flowing in from here. So that's a total of 7 gallons per minute of the fluid flowing into this tank B. But if you look at the outflow, we have 2 gallons per minute flowing out, 5 gallons per minute flowing out here. Outflow is also 7 gallons per minute. Okay, so the rate of change, sorry, not the rate of change, but the 100 gallons in this tank is going to remain 100 gallons, okay? And then finally here we have 1 and 4 flowing out, 1 gallon per minute, 4 gallons per minute, for a total of 5. But we also have 5 gallons per minute flowing in. So the point of going over all that is because, as we've seen in mixture problems before, if the volume of the solution in your tank is changing, as this mixture is happening, that kind of complicates our differential equation. But according to our analysis here, the actual volume of solution across these 3 tanks in each one is constant. The concentration of salt, however, will be changing. Okay, so that's important. Now, let's take a look at this first tank right here. How do we determine a differential equation representing the amount of salt, or the rate of change of the amount of salt in this tank? Well, we have variables x1, x2, and x3 corresponding to the amount of salt in each one of these tanks. And I know that in this case, for example, dx1 dt, so the rate of change in that amount of salt in this first tank, should equal the rate of salt flowing in and the minus the rate of salt flowing out. So we have 2 things flowing into this tank. Okay, I have pure water, which has no salt at all. So that's not going to contribute anything to my inflow. Over here, I have a flow rate of 2 gallons per minute. Okay, but where is this solution coming from? Well, it's coming from tank B. Okay, and if you remember, when we do these mixture problems, to find the rate of flow of salt, it's equal to the concentration of salt in the solution that we're getting that solution from, times the rate of flow of that fluid. So here, our rate of flow is 2 gallons per minute. But what is the concentration of salt in this mixture? Remember, this is just the rate of flow of the solution itself. It's not telling us how much salt is here. Well, it's pulling that solution from tank B. And tank B has, at any given time, x2 pounds of salt in it. That's what x2 represents. Its concentration then would be x2 divided by the volume of that tank. And this is where that initial observation that each tank is going to have a constant 100 gallons in it at any given time matters, because I can just write 100 down here instead of some function of t like we've seen before. So this is the rate at which salt is entering tank A. What is the rate at which salt is exiting tank A? Well, tank A only has one outflow. It's right here, and it's flowing out of the tank at a rate of 6 gallons per minute. What is the concentration of salt in tank A? We're assuming, as we always do in these mixture problems, that each tank is well mixed so that the salt pumps out at a uniform rate. And the concentration of salt in tank A is going to be x1, the total amount of salt in tank A, divided by 100, the volume of tank A. The outflow rate is 6 gallons per minute. So this becomes 6 times x1 over 100. Okay? Simplifying that, I get dx1 dt equals, let's write this term first, negative 3/50 x1 plus 1/50 x2. Okay? Now we need something for dx2 dt. The rate of change in the amount of salt in the second tank with respect to time. So for that, tank B is the most complicated case because we have two sources of salt. We have two inflows and two outflows. Looking at our inflow, here I have 6 gallons per minute of the solution from tank A. As we saw before, that's the same as this, right? This is the solution that was flowing out of tank A, but that same solution is flowing into tank A. So now it's being thought of as an inflow. We have 6 times x1 over 100, but we're also getting salt from this tank here flowing in. A rate of 1 gallon per minute times the concentration of salt in tank C, which, following the same logic as before, would be x3 over 100. This is the net inflow. This is the total of these two inflows here. Now, what about my rate out? Remember, we subtract the rate out, but that's split across these two different outflows. So 2 gallons per minute times, where is this solution coming from? Tank B, where the concentration is x2 over 100. Same thing here, 5 gallons per minute, so that's plus 5 gallons per minute, times x2 over 100, because it's coming from the same place. Okay? These can combine to 7 x2 over 100, and I can simplify things down a whole lot. This is going to give me dx2 dt equals, let's look at how things simplify. Here's my x1 term that becomes 3/50 x1. My x2 terms, if I write that as 7/100 x2, I'm subtracting that. So 7/100 x2 plus 1/100 x3. Okay. Finally, I have dx3 dt. And again, what we're doing is we're looking at the rate of change in the amount of salt in tank C. So what is the inflow in this case? Well, we only have one inflow. It's right here. That would be 5 gallons per minute times the concentration of salt in tank B. That would be x2 over 100. Outflow is split across these two parts right here. So salt is leaving the tank here at a rate of 1 gallon per minute times the concentration of salt there, which is x3 over 100. Here, it's leaving the tank at a rate of 4 gallons per minute times that same concentration, x3 over 100. This simplifies down. If you do some simplification here, this becomes 1/20 x2. Sorry, let me write that differently. dx3 dt equals 1/20 x2. This adds up to 5 x3 over 100, which is minus 1/20 x3. Okay, now this is sloppy. I would probably be better off, taking my results and putting them in one place. But together, these three equations make up that linear system that we're talking about. Okay, in this case, a system of 3 equations in 3 unknowns, because x1, x2, and x3 are the 3 functions that we would be solving for in this case. Okay? All right. I had mentioned we're looking at 2 examples only, so we did the we did the example of the mixture problems. Next, we're looking at circuits. We briefly talked about circuits back in section 1.3. And in that case, we were looking at a closed loop series circuit, and I had mentioned back then that we couldn't derive a lot of the results without doing a lot of background research into electrical circuits and where we're getting some of those little formulas from. But taking a lot of the things for granted that we talked about back then, what we're going to start looking at here are electrical circuits that have more than one closed loop. So here, the E right here is going to represent a source, like a battery or something. Okay, it's going to represent where our voltage is coming from. And using this diagram, and something that we haven't talked about yet, Kirchhoff's first law. So let me actually talk about that. Kirchhoff's first law says that if you have current flowing through a circuit like this, if you look at any particular point, the sum of the currents flowing into that point will always equal the sum of the currents flowing out. And so where we apply that is points in a circuit where the direction splits. So here's what I mean by that. E, this right here is our source, and you can follow the current using the arrows. I1 is the current flowing out. It comes up here, and then we get to this point B1 where the circuit splits into two parts. Okay, and the current going this direction is I2, current going this direction is I3. Kirchhoff's first law would say that I1, the current flowing into that point, is equal to the sum of the currents flowing out. I1 equals I2 plus I3. That's what this is saying right here. Okay, wherever that happens, if you ever have a split in the direction of your circuit, we call that a branch point. So B1 is what we're going to be calling a branch point. Okay. Now, what I want to do is come up with a system of equations that represents the voltage in this circuit. And the reason it's going to turn into a system of equations is because I have two closed loops to analyze here. So I'm going to come up with an equation for each of those closed loops. Okay? And Kirchhoff's second law, second voltage law, which is the one that we talked about, is basically what says that the sum of the voltage drops across either of these loops will equal will be equal to E, this voltage here. So that's what we're using to set up these equations. Okay, so let's start by looking at this first loop right here. Okay, so there's a couple of things that are worth reminding you of. The voltage drop across an inductor. Remember, that's what this little springy looking thing in the diagram is. The voltage drop across an inductor is given by the inductance L times the rate of change in our current with respect to time. So L di dt. And then the voltage drop across a resistor, so we have a couple of resistors in this first closed loop, R1 and R2, is just I times the resistance, I times R, or in this case R1 and R2. So if we apply those and sum the results and set them equal to E of t, which is what Kirchhoff's second law says that we can do, following this path right here, I'm going to have R1 I1, that's the current flowing into R1, so that's this, plus I2, which is the which is the current at this point, times L1. L1 is shown here, so L1 times di2 dt. That's using this, and then that same current I2 is flowing into this resistor as well, R2. So that's I2 R2 using this formula for the voltage drop across a resistor. We've accounted for all components in that first loop, so that would be our first equation right there. Our second loop is this larger outer loop right here. So following that, I still have I1 R1 in the first component here. We're going to go this direction now. I3, whoops, I'm off the screen. So again, starting from E, we're going to have I1R1 as our first voltage drop. This goes this direction. After passing through our branch point, the current becomes I3, and it's going to pass through this inductor. So the current, the voltage drop here is going to be L2, that's the inductance on this inductor, times di3 dt. And then that's the only other component in that circuit. So that's where this second equation in our system is coming from. All right. Now, as is the case with like in algebra when we're dealing with systems of linear equations, this is a linear system as well, because the R1, R2, L1, L2, those are constants. So we have all constant coefficients here. We would like to have the same number of equations as we do variables. We know that that's oftentimes what we need in algebra to solve a linear system. We have an issue here because we have 3 unknowns and only 2 equations. The unknowns are the currents, I1, I2, and I3. But this relationship up here from Kirchhoff's first law allows us to eliminate one of those. So what we're going to do is eliminate I1 by looking for any I1s in our equation and substituting I2 plus I3. Okay? Notice that if you were to do that, so I1 shows up here and here. Substitute I2 plus I3 here, I2 plus I3 here. Distribute that R1 in and then regroup everything. We end up with these 2 equations. Notice in each of these are in fact first order DEs because I have a derivative of I2 and a derivative of I3. I2 and I3 are also the only unknowns showing up now. And then I also have this function of t. So this is a system of linear DEs, first order DEs, in 2 unknowns. And again, we don't know how to solve these things yet, but in Chapter 8 we'll talk about methods for solving these. Like I said, this is a short section. That's all we were needing to cover here. We're going to go ahead and wrap up Chapter 3 now.